Hello students, in this session we are going to see the third part of this psychrometric of air conditioning processes, and a few processes left out, and we have seen the almost all the processes in earlier two sessions, and now we are going to start the part C of this topic. As we discussed, these are all the topics we have seen. Now we are seeing this psychrometric of air conditioning processes. So this air conditioning processes, we have another process that is known as mixing of air streams. So this we are going to discuss in next session. So these are all the processes we are seeing here. So far we have seen sensible heating, sensible cooling, humidification and dehumidification, cooling and adiabatic humidification, cooling and humidification by water injection, heating and humidification process. We have seen humidification by steam injection also. So in this session we are going to see adiabatic chemical dehumidification. So in next session we are going to see adiabatic mixing of air streams. So these are the processes in this particular topic, and we have seen up to seventh one, and now we are going to see the eighth one, and in next session we are going to see the next topic, and that is adiabatic mixing of air streams. So heating and humidification, already we have seen this. So heating and humidification is commonly used in winter air conditioning to warm and humidify air. It is the reverse of cooling and dehumidification. When air passes through a humidifier where spray water temperature is higher than the dry bulb temperature of entering air, so the unsaturated air absorbs moisture and air temperature increases, air becomes humidified and heated. So here heat of vaporization from vapor spray is absorbed, causing air to warm up. Psychrometric chart path, so that is line 1 to 2 shown in the figure, that this is the 1 to 2. So this is 1 to 2 and this is the psychrometric chart, and this is the humidification, vaporization of water spray is absorbed and causing air to warm up, and this is the process is happening here from 1 to 2. So that is TA1 to TA2. So air enters at condition 1 and leaves at condition 2. So this is 1 to 2 here. Here we can see clearly. So this is 1 to 2. Air enters here and this is the sensible heat, and from here it becomes latent heat. So in from 1 to 2 there are two processes taking place. One is sensible heat and latent heat, and the final RH relative humidity can be higher or lower than that of entering air depending on conditions. So mass balance of spray water. So let MW1 and MW2 mass of spray water entering and leaving in terms of kg, and HW1 HW2 enthalpy of spray water in terms of kg per kg, kilojoules per kg. W1 and W2 is specific humidity of entering and leaving air. H1 H2 enthalpy of entering leaving air. MA is mass flow rate of dry air, and mass balance, if you see, the MW1 minus MW2 equal to MA W2 minus W1, or we can also rewritten this as MW2 equal to MW1 minus MA into W2 minus W1, and energy balance So enthalpy balance, in terms of enthalpy balance, MW1 HW1 minus MW2 HW2 equal to Ma into H2 minus H1, and substituting from the first equation we get MW1 HW1 minus MW1 minus Ma W2 minus W1 into HW2. So that is equal to Ma into H2 minus H1, and when we simplify this, H2 minus H1 equal to MW1 divided by Ma, HW1 minus HW2 plus W2 minus W1 into HW2. So this is a simplified equation, and if we further analyze this, heating from point 1 to 3, only temperature rise, and humidification from point 3 to 2, so we are adding the moisture from process 3 to 2, thus Q equal to H2 minus H1, that is equal to H2 minus H3 plus H3 minus H1, so that is equal to QL plus QS. So where QL is latent heat absorbed due to moisture addition, and Qs is sensible heat added to air, and the sensible heat factor, and SHF is SHF equal to Qs divided by Q, so that is equal to Qs divided by Qs plus QL, and that is equal to H3 minus H1 divided by H2 minus H1, and the line that is 1 to 2 in figure B, in earlier figure B, is called the factor line, and heating and dehumidification by steam injection, and steam is injected directly into the airstream used to increase specific humidity quickly. Common in textile mills required high humidity and psychrometric process shown in figure, and the dry bulb temperature of air does not change significantly because steam adds mostly latent heat only. So here in this case, the most heat is latent heat only. And equations, if we say ms equal to mass flow rate of steam and ma equal to mass flow rate of air, w1 and w2 is specific humidities of entering and leaving air, h1 and h2 are enthalpies of entering and leaving air, hs is enthalpy of injected steam. So mass balance, if we see, w2 equal to w1 plus ms divided by ma. So energy balance also can be done here, and that is in terms of enthalpies, H2 equal to H1 plus Ms by Ma into Hs, or we can rewrite this as H2 equal to H1 plus W2 minus W1 into Hs. So this is the diagram, and the steam air is entering here, and air is going out of this chamber, and steam is injected here. So steam is injected here, and this is MS, and this is MA, and this is the air out. So for this 1 to 2 process is the only latent heat instead of the sensible heat. So here the specific humidity is ranging from W1 to W2. So to summarize this, the process heating and humidification, it is spraying water, and steam injection humidification. So here heating and humidification, here equation is mass plus energy balance, whereas steam injection humidification constant enthalpy addition only. So key features in first process is dry bulb temperature and specific humidity both increases, whereas in second steam injection humidification mainly increases humidity, minor temperature rise only. So very little temperature rise we can observe here. So we will see a few examples. Atmospheric air at 25 degree Celsius dry bulb and 12 degree Celsius wet bulb flowing at 100 meter cube per minute. So dry saturated steam at 100 degree Celsius is injected at 72 kg per hour. So find specific humidity, enthalpy of the leaving air, dry bulb, wet bulb temperatures, relative humidity of living air. So living air, we have to find all these parameters at living air only. So given data is TA1 is 25 degrees Celsius, TW1 equal to 12 degrees Celsius, V1 is 100 meter cube per second. So that is the flow rate, and the Ts is 100 degree Celsius, and Ms equal to 72 kg per hour. So that if we convert into minute, it becomes 1.2 kg per minute. So this is the psychrometric chart. It is happening from 1 to 2, and here it is the 0.844 meter cube per kg, the flow rate, and it is the wet bulb temperature is 12 degrees Celsius. At leaving air leaving is that is TW2 we have to find. This is unknown, and this is 25 degree TA1, and TA2 is unknown, that should be find out here, and relative humidity phi2 we have to find. So these are the parameters we have to find, and we most of the parameters can be find out from psychrometric chart itself. So specific humidity from psychrometric chart, specific volume. So for this VS1 0.844 is the VS1 is obtaining from psychrometric chart is 0.844 meter cube per kg of dry air. So this is VS1. It is the specific volume at entering, and specific humidity at point 1, that is the air entering into the stream. So that is W1 equal to 0.0034 kg per kg of dry air, and mass flow rate MA equal to V1 divided by VS1. So that is equal to 100 divided by 0.844 meter cube. So that is equal to 118.5 kg per minute. So specific humidity after steam injection. So W2 equal to W1 plus Ms by Ma. So W2 can be find out. So that is 0.0135 kg per kg of dry air, and enthalpy of leaving air from steam tables Hs equal to 2676 kilojoules per kg, and energy balance H2 equal to H1 plus Ms by Ma into Hs. So we can find out from this equation, because we know H1, Ms, Ma and Hs, and now from this we can find out Hs equal to 61.3 kilojoules per kg of dry air. And final air properties from psychrometric chart: dry bulb temperature Ta2, so that air leaving is Ta2 equal to 26.1 degrees Celsius, wet bulb temperature Tw2 equal to 21.1 degrees Celsius. So relative humidity pi2 equal to 62%. So these are the unknown parameters we can find out from psychrometric chart. So next numerical we will see here: moist air at 5 degrees Celsius dry bulb and 2.5 degrees Celsius wet bulb flows at 90 meter cube per minute. So that is 1.01325 bar pressure. So at this pressure it is flowing, and the sensible heat is given as 40.7 kilowatts, and steam injection is 40 kg per hour of saturated steam at 110 degree Celsius. Find dry bulb and wet bulb temperatures after process. So at leaving we have to find, and Ta1 the given data is Ta1 equal to 5 degrees Celsius, Tw1 equal to 2.5 degrees Celsius, V1 equal to 90 meter cube per minute, P is the pressure 1.01325 bar, and sensible heat equal to 40.7 kilowatts. Steam mass equal to 40 kg per hour. Steam temperature is 110 degrees Celsius. So this is the psychrometric chart, and it is happening from this point 5 to 2 to 3. So now the here 2 to 3, from 1 to 2 it is only the constant specific humidity, whereas 2 to 3 the humidity varies, and we have to find the 3, 4 and 5. So we have to find Ta2, and that is the entering leaving, and we have to find the Tw2 also, Tw2. So here So from psychrometric chart, specific volume equal to Vs1, so that is 0.792 meter cube per kg of dry air, and the specific humidity can be find out. Specific humidity W1 equal to 0.0035 kg per kg of dry air, and enthalpy is H1 equal to 13.8 kilojoules per kg of dry air. So mass flow rate Ma equal to V1 divided by Vs1, that is equal to 90 divided by 0.792 equal to 113.636 kg per minute. So that is in terms of kg per hour 6818. So specific humidity at leaving, so W3 equal to W1 plus Ms by Ma. So specific humidity can be find out. W3 equal to 0.0094 kg per kg of dry air. So enthalpy of leaving air from steam tables Hs equal to 2691.3 kilojoules per kg, and energy balance H3 equal to H1 plus Ms by Ma into Hs plus Qs by Ma. So by solving this, we are getting H3 equal to 51.1 kilojoules per kg of dry air. So final air properties are from psychrometric chart. Dry bulb temperature Ta3 equal to 26 degrees Celsius, and wet bulb temperature Tw3 equal to 18.5 degrees Celsius. So these are the final. So we will see next problem, numerical. It is the outdoor air at 10 degrees Celsius dry bulb and 30% of relative humidity. The flow rate equal to 45 meter cube per minute, heated to 22 degrees Celsius, then humidified to 25 degrees Celsius dry bulb, and 60% of relative humidity. So find rate of heat supply in heating section, mass flow rate of steam in humidification section. So given data is Ta1 equal to 10 degrees Celsius, pi equal to 30%, V1 equal to 45 meter cube per minute, Ta2 equal to 22 degrees Celsius after heating, Ta3 equal to 25 degrees Celsius, pi equal to 60% after humidification, Pb equal to 1 bar, so that is 10 to the power of 5 Newton per meter square. And this is the process. So from 1 to 2 is it is happening at constant specific humidity. From 2 to 3 it is the variable humidity, specific humidity, and we have to find. We know that at point 1 it is 10 degrees Celsius, so that is dry bulb temperature Ta1, and Ta2 is 22 degrees Celsius, and Ta3 is 25 degrees Celsius. Now we have to find H1 H2 also, and we have to find Ta3. So that is the dry bulb temperature, wet bulb temperature at 3. So we have to find these parameters. So solution is step 1, humidity at point 1. So from steam tables, Ta1 equal to 10 degrees Celsius, and for this the saturation pressure Psat1 equal to 0.01227 bar. So in terms of Newton meter square, it is 1227. So relative humidity relation pi1 equal to Pv1 divided by Psat1. So we can find Pv1 equal to 0.003681, and specific humidity is, we can find now substituting all these values, we can find the specific humidity is 0.0023 kg per kg of dry air. Coming to next step, the specific volume and mass flow rate we have to find, and the pressure of dry air Pa equal to Pb minus Pb1, so that is equal to 0.996319 bar, and the specific volume Vs1 equal to RTA1 divided by Pa. So now substituting all these values, we are getting specific volume equal to Vs1 equal to 0.815 meter cube per kg. So mass flow rate Ma equal to V1 by Vs1 equal to 45 divided by 0.85815, so that is equal to 55.2 kg per minute. So enthalpy at point 1 and 2 we can find out very easily. So H equal to 1.005 Ta plus W into 2500 plus 1.9 Ta. So at point 1 we can find out it as 15.84 kilojoules per kg. At point 2 the same equation can be applied and H2 will become 27.96 kilojoules per kg. So rate of heat supply, so that is Q equal to MA H2 minus H1, so that is 669 kilojoules per minute. In terms of watt, it is 11.15 kilowatts. And mass of steam for humidification, so at 25 degrees Celsius, saturation pressure Psat 3 equal to 0.03166 bar. So partial pressure PV3 equal to zero point 0.6 into 0.03166. It is coming as 0.019 bar, and specific humidity at 0.3 W3 can be find out. We know all these values, so we can directly find it as 0.012 kg per kg of dry air. And mass flow rate of steam ms equal to ma w3 minus w2. So where since w2 equal to w1, we can substitute this, and 55.2 into 0.012 minus 0.0023, that becomes 0.535 kg per minute. So this is the specific the mass specific humidity at point 3. And mass flow rate of steam is 0.35 kg per minute. So next numerical, atmospheric air at 16 degrees Celsius, dry bulb temperature and 25% relative humidity passes through a furnace and a humidifier. Final dry bulb temperature is 30 degrees Celsius. Final relative humidity is 50%. So find heat added, moisture added, sensible heat. So that is SHF also to be find. And the given data is TA1 equal to 16 degrees Celsius and TA2 is 30 degrees Celsius, and pi 1 is 25. Relative humidity at point 1 is 25% and at point 2 is 50%. So here this is a point 1 at 25% and at 50%. So we know TA1 is 16 and TA2 is 30 degrees Celsius. Heat added to air from psychrometric chart, enthalpy at point 1 H1 equal to 23 kilojoules per kg of dry air. Enthalpy at point A, HA equal to 38 kilojoules per kg of dry air, and enthalpy at point 2 equal to H2, so that is 64 kilojoules per kg of dry air. So these data we can easily find from psychrometric chart. So heat added is H2 minus H1, so that is nothing but 41 kilojoules per kg of dry air. So moisture added to air is the specific humidity at point 1, so W1 equal to 0.0026, and at point 2 is 0.0132 kg per kg of dry air, and we can find moisture added is W2 minus W1. So here specific humidity at point 2 is 0.0132 minus at point 1 is 0.0026, so that becomes 0.0106 kg of dry air. So this is the moisture added. So we have find the heat added and then moisture added, and then we have to find the sensible heat factor SHF. So that is SHF equal to HA minus H1 divided by H2 minus H1. So that becomes 0.366 is the sensible heat factor. So next example, air at 10 degree Celsius dry bulb temperature and 90% of relative humidity is heated to 35 degrees Celsius of dry bulb temperature and 22.5 degrees Celsius of wet bulb temperature through a process involving preheating and humidification. So preheating is taking place here, and preheating temperatures we have to find total heat requirement, makeup water required and humidifying efficiency. So these four parameters we have to find. So the given data is Ta1 equal to 10 degrees Celsius, pi 1 equal to 90%, Ta2 is 35 degrees Celsius, that is the final dBt. TW2 is equal to 22.5 degrees Celsius, so that is final WBT. So here this is the point 1 and up to point B is happening, and then it is a constant specific humidity process from B to 2. So when we draw from the point B through H, so that becomes HA, and the air entering is H1 and air leaving is at H2. So in between we have state B, so we have to find the parameters at B also. So now the TA also we need to find. So TA for point A also we need to find, and the solution is very simple, and temperature to preheat. So from psychrometric chart, Ta equal to 32.6. So Ta is 32.6 degrees Celsius, and total heat. So preheating, temperature to preheat is 32.6, and total heating required. So that is nothing but at point 1 H1 equal to 27.2 kilojoules per kg, and enthalpy at point A is 51 kilojoules per kg. So enthalpy at point 2 H2 equal to 68 kilojoules per kg. So preheating heat is can be find out from HA minus H1. So that is 23.8 kilojoules per kg. So preheating heat is H2 minus HB. So that is 17 kilojoules per kg. Total heat required 23.8 plus 17. So that is 40.8 kilojoules per kg. Makeup water required is specific humidity W1, W2, we know both, and we can find out from this W2 minus W1 equal to 0.0054 kg of dry air. So humidifying efficiency is the TWB is 19.1 from psychrometric chart, and TWB dash is 18 degrees Celsius. And if we know this, the efficiency can be find out from Ta minus Tb divided by Ta minus TWB dash. So substituting all these values, we are getting 92.4 percentage. So this is the final answer. So heating and dehumidification, it is adiabatic chemical dehumidification process. So mainly used in industrial air conditioning and comfort installations where a low relative humidity or low dew point is required. And this process is air is passed over chemicals. So chemicals are used. So those can be absorbents or absorbents. So here that remove moisture from air by condensation process. So here process is air is passed over chemicals. So that can be absorbents or absorbents. So that remove the moisture from air by condensation process. Key points to remember here: specific humidity decreases, dry bulb temperature increases due to the release of latent heat of condensation, and path on the psychrometric chart along the constant wet bulb temperature line, initially ideal case. So but due to release of latent heat, actual process deviates slightly upwards. So that I will show you in figure. So effectiveness or efficiency of dehumidifier equal to Ta3 minus Ta1 divided by Ta2 minus Ta1, where Ta1 is entering at dBt. So dry bulb temperature. Ta2 is ideal dBt after complete adiabatic process. Ta3 equal to actual dBt after chemical dehumidification process. So heat of absorption is released, so that is sensible heating occurs. And types of chemicals used here are absorbents change physically, chemically. So absorbents, they normally change physically and chemically. They are calcium chloride, lithium chloride. So absorbents, So adsorbents are solid substances, so like a silica gel, activated alumina, so that remove moisture without chemical change. So adsorbents also used. So this is the chemical process, and this is one example. We will see examples on this. This is the last process in this topic, and mixing of air streams we are going to take up in next session. So saturated air, so given our Ta1 equal to Tw1 is 21 degrees Celsius. Final relative humidity is also given 20 degrees Celsius, sorry, 20 percentage. So find Ta2 heat rejected, final RH after cooling, final dew point, moisture removed. So we have to find these parameters: Ta2 heat rejected, final RH, final dew point, moisture removed. And first one is temperature of air at end of drying process. So from psychrometric chart we can see Ta2 equal to 38.5. So heat rejected during cooling process. So H2 equal to 61 kilojoules per kg of dry air, H3 equal to 43 kilojoules per kg of dry air. Heat rejected H2 minus H3, that is equal to 61 minus 43, 18 kilojoules per kg. Relative humidity at end of cooling from the psychrometric chart, pi 3 equal to 55 percentage. So dpt at end of drying, so from same psychrometric chart, dp2 can be find out as 11.6 degrees Celsius. Moisture removed during drying from same psychrometric chart, w1 is 0.0157, w2 is 0.0084 kg per kg of dry air, and thus moisture removed is W1 minus W2, so that becomes 0.0073 kg of kg dry air. So now the all these concepts we have seen. Effectiveness of chemical dehumidification, so that is nothing but efficiency, and moisture removed during drying, so W1 minus W2. Heat rejected during cooling is H2 minus H3. Dew point at end of drying from psychrometric chart at point 2, and final relative humidity after cooling is the psychrometric chart at point 3. So this is the summary. You can remember this table and easily you can solve this problem. This is the summary of the important concepts. So next problem, that 300 meter cube per minute of air is supplied from outdoor conditions of 40 degrees Celsius dry bulb temperature and 26 degrees Celsius wet bulb temperature. The air undergoes dehumidification first by a cooling coil with bypass factor 0.32 and ADP equal to 15 degrees Celsius, and the followed by chemical dehumidifier at 30 degrees Celsius dry bulb temperature, then again passes over another cooling coil with the surface temperature 15 degrees Celsius and bypass factor is 0.026, and we have to calculate the capacities of two cooling coils and dehumidifier. So this is the process, entire process is happening here, and this is 1 to 2, in between we have 3, and 3 is projected here, and 4, 5, 6. So this is the entire process. So for this we have to find the all the cooling capacities, that is the capacities of two cooling coils and dehumidifier. So once you get this values, you can easily solve this from psychrometric chart. So mark the process on psychrometric chart. So plot initial outdoor condition point 1 at 40 degrees Celsius and 26 degree wet bulb temperature. So wet bulb temperature is 26 degrees Celsius, and draw a horizontal line to meet the saturation curve at point 2. So ADP is given, that is 15 degrees Celsius. Locate point 3 such that, so length of 2 to 3 is equal to 0.32 into length of 1 to 2, and point 3 is the air condition after first cooling coil. So draw constant enthalpy line to 30 degrees Celsius dBT at point 4 after chemical dehumidification. So from point 4 again follow horizontal line to meet vertical line at 15 degrees Celsius dBT at zero point 0.5. So locate zero point 0.6 such that the length of 5 to 6 is 0.26 into length of 5 to 4, and zero point 0.6 is the condition of air after second cooling coil. So capacities of two cooling coils. So from psychrometric chart, specific humidity at zero point 0.1 is can be found out, that is 0.0156 kg of dry air, and enthalpy at zero point 0.1 H1 equal to 80.6 kilojoules per kg of dry air. So this is from psychrometric chart again, and specific volume also can be found out, Va1 equal to 0.94 meter cube per kg. Enthalpy at subsequent points can be found out, H3 equal to 54.5, and H4, so that is also equal to H3 54.5 kilojoules per kg of dry air, and H6 is 43 kilojoules per kg of dry air. Specific humidity at zero point 0.4 is W4, so that is 0.0094 kg of dry air, and mass flow rate is MA V1 divided by Va1, we know both, so substituting those values, it becomes 319 kg per minute. So capacities, first cooling coil capacity is MA into H1 minus H3, so that is 8326 kilojoules per minute, and second cooling coil is MA into H4 minus H6. So by substituting these values, we get the second cooling coil capacity equal to 3668, so 3668 kilojoules per minute. So capacity of the dehumidifier we have to find. So dehumidification capacity is based on moisture removal only. So remember this, dehumidification capacity is based on moisture removal. So capacity equal to MA into W1 minus W4. So substituting the values, we get 1.98 kg per minute. So these are the topics in this particular topic. We have seen in three different parts. We have divided this one topic into three parts, and we are completing the last but one topic in this session. In next session, we will see a very simple topic, mixing of air streams. We will see in next session. And textbooks, please refer RS Kurmi book, and for additional information you can refer Rajput, and you can refer CP Arora also. So we stop here, students. In next session we will see the air mixing of different air streams. So that is only topic left out in fourth unit. We will meet again, we will complete that topic. Thank you, students.